Hi, my name is Zoe, and today we're going to be reviewing one of my all-time favorite EECS 203 topics, which is mathematical induction. So basically what mathematical induction is a proof method, kind of like how we've been talking about direct proofs, like proof by contradictions for a while. And we use mathematical induction usually to prove something that's true for like all of a set, or more specifically to prove like a series of implications. So mathematical induction comes in two steps, the first of which is the base case, and the second is the induction step. And we're going to use like these two steps to basically prove that we can like climb up a whole ladder of implications. So the base case proves that we can definitely get onto the first rung of the ladder. So given that like this bottom part is true, we can definitely get onto the bottom part of the ladder. And what the induction step proves is that if we're on any arbitrary kth rung of the ladder, we can definitely make it up to the k plus first rung of the ladder. So by proving that we can get to the bottom and that on any arbitrary rung we can definitely get to the next rung, we've proven that we can make our way all the way up the ladder, if that makes sense. So more specifically with the induction step, how it works is if you remember our natural deduction rules, we said that if we have P and we can do some stuff and then arrive at Q, we can conclude that P implies Q. And then this could just be applied to this ladder by saying that if we assume P of K, meaning that we can hop onto the kth rung of the ladder, and then we can do some stuff and arrive at the P of K plus first rung of the ladder, then we know we can get from one to the next no matter what. And then also that it applies to every rung on the ladder, because remember when we pick an arbitrary element of K, it applies to like for all in the set. So now that we understand conceptually how mathematical induction works, let's go through a specific example. So today we're going to prove that for all of the natural numbers, so for any n that exists in the natural number set, that the sum of the first n natural numbers is equal to n times n plus 1 over 2. And we can expect this to be true because we're familiar with this relationship from like our summation rules. So what we're going to do first then is start with the base case. The lowest natural number in this case is, of course, 0. So we're just going to substitute 0 in for n and make sure that this equality matches up. So we can do the sum of the first n natural numbers, which is 0, is equal to 0 times 0 plus 1. We're just plugging it in over here. And that is 2 over 0 equals 0. So that's true. We know the base case holds because P of 0 is true. So now we're ready to move on to our induction step, which has a lot more things in it. So remember, the first thing we do with our inductive step is we assume P of K. And in this case, P of K is just what we can get when we put in K for n. So 0 plus 1 plus 2 plus K is equal to K plus 1 over 2. So we're saying that this is like for sure true. And what we ultimately want to show is P of K plus 1. And we know that P of K plus 1, we can get it from us putting in a K plus 1 anywhere we see a K in this expression. So it's just 0 plus 1 plus whatever plus K plus 1 is equal to K plus 1 times K plus 1 plus an extra 1 over 2. So basically what we want to do then is just mess with one side of this equation until we can get them both to match. And I'm picking for us, we're going to mess with this side. It's usually easier when it's a sum like this. Instead of trying to make this into a bigger thing, it's usually easier to condense one thing. So what we know about this expression so far is we actually know from our inductive hypothesis, which is just another word for P of K plus 1, that the first K natural numbers are equivalent to this. So we can actually rewrite this expression. If we take out this whole part right here and just substitute in this, we know that K times K plus 1 over 2 plus this gets carried down plus K plus 1 is equal, well, we're going to figure out what it's equal to. We want to prove it's equal to this. So basically what we're just going to do now is mess with some arithmetic until we make this look like that. So I'm just going to rewrite this so we can like combine the fractions. So that's K plus 1 times K plus 1 over 2 plus 2K over 2 plus 2 over 2. And that's when we like put this all together, then we get K times K plus 1 plus 2K plus 2 over 2. And then we can factor out a 2 on this side. So that's K times K plus 1 plus 2 times K plus 1 over 2. Factor out this K plus 1, we get K plus 1 times K plus 2 over 2. And then basically I'm just going to mess with this so it looks like that. Like obviously this is like algebraically simplified, but if we just take this 2 and write it as 1 plus 1 instead, then it's like really clear to your grader that we have proven now that this expression, we made it into this, and we've proven that it's definitely equal to this. So therefore, we have proven that P of k implies P of k plus 1. And we've proven that P of 0 holds, and therefore we've proven by mathematical induction that this equality is in fact true. Thank you.